All right. Hello, Professor. My name is Jay Grillo, and this is the recording to my lab final video, along with my one page on what I learned through all the labs. I will be going over what I did for this Simulink model. So let me share my screen. So basically, this is the top model, and then the one without the transformers is down below. It looks like I have a lot, and I definitely do in here. Most of them, however, are just like power meters and things to be able to get the data out that I want. So just to go over it a little bit, we have our generator over here, which is our source basically for our voltage and current. Um, this is our input voltage, and then this is our like prime mover sort of like input power. Um, what we're getting out of that, we're seeing that 208 again, which is good. Um, I was struggling with it for a while, getting errors of why it wasn't running, and I did some research. And apparently, when you connect this system to a transformer, you're going from more of a current-based solution to then like voltages in here. So I had to toss a um, just a parallel RLC load, but just a resistive load in parallel with that. And then also on the other side, going to my motors over here. So basically, we're going in at 208 volts, and then we're stepping up to 470. And then we have a 10 ohm resistive load here, which is like our line where we're getting a little bit of power loss. And this is something where when we step back up or step back down the voltage to 208 again, and we connect another resistive load here, we are losing a little bit of power. I think I set them both to just like 1 watt, which I'm pretty sure means that we're just pulling 1 watt out of the system, and it shouldn't really affect it that much. It's just more for the solution. And then over here is where it gets kind of complicated with the wiring. We have Sorry, it's not letting me scroll very easily, but we have our induction motor over here that's connected in parallel to our synchronous motor down here. And basically what's going on is the induction motor is, when it runs, it's basically consuming some bars that we need to be able to supply. That a lot of times when you're trying to correct a power factor, you're connecting some sort of capacitor bank. But it's pretty cool that instead we can use a motor that's a synchronous motor instead to be able to do that. So I found for the RPM to not basically disengage, I had to go at about 1.3 Newton meters before the motor like loses its slip is too great. And then I used I went in here to tools and did the load flow and was able to solve the system to get the power factor to be 1. When it did that, it was also changing. I had to make this a swing load as well. It was changing my values over there, so I just changed them back. But then basically what it ended up being was 75 for the input voltage over here. And then when I tossed the MATLAB, let me pull that up. Over here, so I put it in as 200 instead of 250 because I decided that this motor up here would also need some power. So I dropped it from what we were actually putting in. That made sense in my head. So if I put in 75 here and we run this, we get 1.836 or 1.836 that I then tossed into our parameters to be able to get this angle correct. So then when we run it, oops, pull that back over here. When we run this, it might be slow with Zoom. But basically this is our total power factor. And then these are the power factors of the 2 motors that I connected over here. So you can see that they kind of sum to this power factor of 1 that's pretty consistent across the board. And I was liking what I was seeing here because our RPM for this motor is below the 1800, which is good. That means we're consuming power. And down here, our electrical power is -2. So I liked what I was seeing there. So then when I took these values, basically I have all of these out plugs to be able to get those graphs, then also calculate or be able to show me what our powers are and our Qs for everything. If I pull that over, let's see, where's the word? So basically for the first model, these are my EA and delta that MATLAB was able to calculate for me. And then this is the P source and Q source. And then these are all the values for the different motors. And basically what I did was I just root sum squared to find like the total power, and then put the out over the in and found the efficiency to be 77.1, which sounded low to me, especially using the transformers. I think there might be something wrong with how my basically my system is producing the power. And when I was doing the load flow solver, it was kind of getting hung up on that. But anyway, we can comment all of this out, but we need the power GUI still. So down here, I copied the same system, but instead added, yeah, he's still good. Instead took out the transformers. So I left the resistive load in there so we could still see what the line would look like if we're dissipating power just at the higher current, lower voltage, which should mean that our efficiency should be lower. So, and on this one, it was working for me best when I run it for 30 seconds because the induction motor does some weird stuff where it takes forever to speed up on my model. And I'm not exactly sure why. So let me get rid of these. And then again, this is what the load flow solver was able to give me. And then I was able to go in and put in what I needed over here to be able to get the power that we want and the voltage. So you can see when we first start up, it's pretty high. And our RPM right now is 783, which is good. That means our induction motor is working how it's supposed to. But the power factor, even with the solver, is still dropping kind of weird. So it looks like it starts to approach 1, which I'm not exactly sure why. It just keeps dropping. But as long as it would reach 1 at some point, I'd be happy with it. And then and for this one, I did the same thing that once I got what my EA should be, I just checked to make sure that the delta that it was solving and putting in there was good. Also, as well, I should talk about, I changed up here, I looked at the Q that the induction motor was producing and then matched that in the load flow for a reactive power generation. And I did the same thing for down here with a different Q. So you can kind of see that it's going towards 1. But yeah, basically, I don't want to make you have to watch a really long video. I could definitely talk about it more, but oh, there it is. Yeah, so then I put in the EA delta and then put in all of my parameters that I found, and then calculated the efficiency to be 61.5. So that's good. It's lower. It means it makes sense to me when we're dropping the transformers. You're going up, or you're no longer going up. So we're going to have a higher current that's going to dissipate more power through that 10 ohm resistor. So yeah, it makes sense that the power is dropping there. They're still both a little low in general, but I'm not really sure if that's characteristic of these types of systems. These values definitely seem kind of skewed to me, but I've put in a lot of time to this model. It got pretty complicated, so I think this is the best I'm going to be able to get it to be. Yeah, if you have any questions about it, please feel free to reach out. Otherwise, I'll just submit this video with the PDF that I'm going to put out, and have a great winter break. Thanks.